Okie doke, so today we're going to look at square numbers and properties of square numbers and their differences and all sorts of stuff. So the first one, 20 squared, let's have a look at that. 20 times 20, well if I just thought of it as 2 tens times 2 tens, 2 twos are 4, tens times tens is hundreds, so it's going to be 400. If I go to 19 squared, I've shown two different ways of doing it here. You could have chosen other numbers. Whatever works for you, whatever times tables you know is what works for you. So here I've done 20 take away 1 is 19, 20 take away 1 is 19. So let's have a look. We know that 20 times 20 is 400, 20 times minus 1 is minus 20, minus 1 times 20 is minus 20, minus 1 times minus 1 gives me plus 1. So 400 take away 40 is 360, plus 1 is 361. If I wanted to do an addition, I didn't want to do the subtraction, that's fine. Here's another way you could have done it. So instead of 19, I've got 10 and 9. So 10 and 9, 10 and 9. So I've got 10 tens are 100, 10 nines are 90, 9 tens are 90, and 9 nines are 81. So I've got 100 plus another 180 is 280. Plus another 80 is 361. Same answer. Phew. If I was doing 18 squared, let's have a look at 18 squared. Well, this time I've chosen to bust up the 18 into 9 plus 9. So I've just got two lots of 9 and then 9 here as well. So 9 times 9 is 81. 9 times 9 is 81. 9 times 9, 9 times 9. So 81 times 4. 80 times 4 is 320, and 4 ones are 4, so 324. Last one, 17 squared. So this time I've chosen to break up the 17 into 12 and 5. So I've got 12 12s is 144, 12 5s is 60, 5 12s is 60, and 5 5s is 25. So I've got 144 plus 120 is 264, plus another 25 is 289. So we're going to use those numbers in the next little example. So now we're going to use these numbers that we just made, and we're going to look for some patterns and see if we can find something in the patterns that makes maths really, really cool. So if I said to you 20 squared take away 17 squared. Alright, so 400 is 20 squared, 17 squared was 289. Difference between those two is 111. So what they did was they looked for patterns and they said, well, what's 20 plus 17 and 20 minus 17? What does that give us? And so 20 plus 17 is 37, 20 take away 17 is 3. 3 lots of 37 is also 111. It's like, is this a coincidence or is this, something that happens all the time? It's pretty cool to do something as complicated as 20 squared and 17 squared, in the days before calculators and stuff. That's pretty tricky. But the hardest thing I've got to do now is just multiply 37 by 3. 3 lots of 30, 3 lots of 7, 90 and 21. Piece of cake. Let's have a look at another one. 19 squared minus 18 squared. So 19 squared was 361. 18 squared 324. 19 squared 361. 18 squared 324. Difference between those two is 37. 19 plus 18 is 37. 19 minus 18 is 37. Works again. How cool is this? And then you might say, well, does it work for all numbers? Let's try a different one. If I said to you 19 squared minus 93 squared, in the days before a calculator, that would have been yuck. But what I can do is say, all right, let's do 97 plus 93 and 97 minus 93. 97 plus 93 is 190. 97 minus 93 is 4. It's got a difference of 4. And if I thought about, 4 lots of 200, that's 800, and then just take away 4 lots of 10, 760. Pretty cool. Pretty cool. So then mathematicians decided, is this, what's the general case, or what's the general rule? How can I make all of that explainable for all numbers? So how they wrote that was, and if you see up here, I've got a little a and a little b. Right, so a is the first number. So, a squared minus b squared. So in the second example, this is a and this is b. In this example, this is a, this is b. So a squared minus b squared is always a plus b, a minus b. That's the rule for a difference of two squares. So choose two numbers and find the difference between their two squares, just like I did over here, and prove it for yourself. So here we are with the picture of what all of that really looks like for any two numbers. If I've got a squared minus b squared, any two numbers, finding the difference between their squares, it equals a plus b, a minus b. Let's have a look at how that works as a picture and why it works. So along the top I've got a plus b. Along the side I've got a minus b. So this is a plus b, this is a minus b. I've written that here in green. Alrighty, so what have we got? A times a gives me a squared. A times b gives me ab. Minus b times a gives me minus ab. And minus b times plus b gives me the negative of b squared. Can you see that these two, if I add them together, ab minus ab, just cancels each other out, and all I'm left with is a squared minus b squared. So a plus b times a minus b equals a squared minus b squared for any two numbers a and b. That's pretty cool. Let's do an example with some letters and numbers. So if I've got d squared minus 81, I've got to think of the 81 as 9 squared because it has to be a difference of two squares. And as long as I'm thinking of 81 as 9 squared, I can just write down d plus 9, d minus 9. The picture is over here on the right. There's my d plus 9. Here's my d minus 9. So d times d gives me d squared. D times 9 gives me 9d. D times negative 9 gives me minus 9d. And minus 9 times 9 gives me minus 81. Not plus 81. Just checking to see if you were awake. So that's a minus 81. So what am I left with? Well, 9d minus 9d cancels each other out. All I'm left with is d squared minus 81. So I know that it's true. The last example that I've got is one that's got a lot more letters in it. Oops, I've lost a bit of it. Hang on, let me put that back. So I've got 4k squared minus 9m squared. So I need to think of them as squares. So let's think. 4k squared, well I know that 2 squared is 4 and k times k is k squared. So I'm thinking of 4k squared as 2k all squared. 2k times 2k, 4k squared. 2 2s are 4, k times k is k squared. The 9m I'm thinking of as 3m all squared, because 3m times 3m is 9m squared. So what I can write for this is 2k plus 3m, 2k minus 3m. And that's all you need to write when you're doing difference of perfect squares questions.